Welcome to Senseren's seminar on Novel Flow Sensor Platform for Smart Meter Dose Inhalers. Senseren is a world leader in electronic sensors, offering solutions for several applications, including the medical field, and covering flow, gas, and fine particle sensing. My name is Haykel Ben Jama. I am a key account manager at Senseren in the medical field, with a major focus on respiratory devices. I am glad to guide you today through this presentation. Asthma affects 340 million adults and children globally and accounts for an estimated 400,000 deaths every year. Adherence rates are estimated to average around 50%. Poor adherence is associated with considerable asthma-related morbidity. Also, the risk of an asthma exacerbation is more than 3 times higher in patients after cessation of low-dose inhaled corticosteroids. The cost of treatment of asthma increases significantly with exacerbation. The treatment of uncontrolled asthma cases in Europe costs 4 times more than the treatment of well-controlled cases. Metered-dose inhalers account among the most important ways to dispense drugs to asthma patients. The patients using metered-dose inhaler are more likely to make at least one error compared to users of dry powder inhalers. Metered-dose inhalers appear to be more challenging to use. In the rest of the presentation, we will only focus on metered-dose inhalers. Inhaler errors made by patients include incorrect positioning of the inhaler, or forgetting to remove the cap or shake the device, failure to exhale before actuation, failure to inhale and hold the breath correctly, and a missing or badly coordinated actuation of the inhaler. Results of a study performed in 2012 showed that 76% of the patients using metered-dose inhalers made at least one error. By monitoring the patient utilization of the metered-dose inhalers, how can we help the patient improve the drug intake? How can the practitioner predict and avoid an exacerbation of the disease? How can the practitioner, pharma company, and payers understand if the drug was used correctly? In order to answer the previous questions, we propose to monitor the inhalation flow profile of the patient during the utilization of the metered-dose inhaler. This aims at understanding whether the drug was released within the optimal window of the inhalation cycle and how the course of the disease is evolving over time. By measuring the inhalation airflow profile, we can determine whether the patient entirely exhaled before inhaling. We can also measure the depth and length of the inhalation and verify if the patient's breath is slow enough. On the other hand, we can use the inhalation flow profile in order to assess the lung function by deriving the peak inspiratory flow rate, the inhaled volume, the airway resistance, and the inspiratory part of the spirometry curve. The obtained results allow us to monitor every inhalation for its quality and the correct use of the inhaler, and additionally gather feedback on the course of the disease and effectiveness of the medication without additional patient effort. Let us have a deeper look at the technical implementation to perform the previously mentioned measurements. We used one of our differential pressure sensors, the STP3X, also used as a flow sensor. This is the latest generation of small footprint, low power, and high accuracy flow sensors. We attached the sensor to a metered-dose inhaler. According to the Bernoulli-Venturi principle, the pressure drops at the MDI inlet during inhalation. A portion of the air flows through the flow sensor. The extreme sensitivity of the sensor STP3X gives an accurate flow that correlates to the inhaled airflow through the MDI. By doing so, we created no interference with the inhaler flow channel, and we caused no change in the inhaler flow resistance, so that the drug delivery would not be impacted by the flow measurement. We took advantage of the small size of the sensor of 5 by 6 by 9 mm in order to embed it in a small and detachable clip-on device to the MDI. The clip-on device was designed and 3D printed. The design of the PCB included, in addition to the flow sensor, a Bluetooth and microprocessor module, as well as a cell battery. We completed the electronic design with an accelerometer in order to detect the MDI shaking. The clip-on device transmits the results to a smartphone application that processes the data and generates the flow profile and lung function. We can see here the side and top views of the green clip-on device attached to the inhaler. By zooming into the top view, we can see the optimized design of the flow channel with 4 openings for a larger flow and therefore a higher sensitivity of the measurement. The measurement principle of the clip-on device is based on the correlation between the airflow through the flow sensor and the airflow through the inhaler. In order to obtain the correlation factor for different flow rates, we calibrated the clip-on device by using one of our mass flow meters, SFM3000, as a reference, translating the pressure in Pascal into flow signal in liter per minute. Following this calibration step, we made a control experiment consisting of comparing the clip-on flow sensor signal to the reference. The curve to the left shows a very good agreement. We also compared the total measured volume to a syringe pump reference of 3 liters. The results to the right show a good agreement with 1% error. The calibrated results are sent from the clip-on sensor to an application on a smartphone, which exploits the results numerically. In this curve, we can see the inhalation profile of the patient over time. The optimal actuation window can be identified on the curve shortly before the peak inspiratory flow rate. The accelerometer that we included in the clip-on sensor detects the actuation and moment of drug release. The moment can be compared to the optimal actuation window in order to conclude whether the actuation was performed correctly. The inhalation profile gives an indication whether the patient inhaled slow and deep enough. In the next curve, we identify the peak inspiratory flow rate. The integration of the flow rate over time gives the total inhaled volume. In the next curve, a calculation of the airway resistance is performed. The airway resistance is defined by the ratio of the time needed to increase the flow rate from 10 to 90% of the peak inspiratory flow rate, divided by the value of the said peak inspiratory flow rate. Finally, the measured results were exploited as flow rate versus inhaled volume instead of time. This yields the inspiratory side of the spirometry measurement. All these parameters are powerful results to assess the lung function. Last but not least, I would like to explain how the previously shown measurement results can be exploited in future directions to monitor the drug delivery and the course of the disease. Several research groups have shown that monitoring peak inspiratory flow rate, peak inspiratory airflow, the inspired volume, and the airway resistance over time allow to predict the next exacerbation, as shown in the exemplary data above. Also, the GINA recommendations state that the lung function is a reliable indicator of the severity of the exacerbation. Collecting and analyzing the data can provide an insight on the patient's compliance, the correct use of the inhaler, the effectiveness of the medication, and the course of the disease. The ability of the data of the patient or the availability of the data of the patient will help them improve the medication intake. With this data, the doctors can prevent the next exacerbation, control the quality of the drug intake, and adjust the drug dosage accordingly. The pharma companies and the health payers can also understand the efficacy of the drug in the field by exploiting such data. Now I would like to move on to the summary and conclusions. Asthma is a global concern with many casualties and high treatment costs. Monitoring the drug delivery and lung function promises an improvement of the adherence to the therapy, visibility on the course of the disease, and understanding of the drug efficacy. We developed a flow meter clip-on MDI, a clip-on for MDIs, using our flow meter SDP3X, enabling the measurement through an MDI without impacting the inhaler flow path. Measurement results of the clip-on show good agreement with the flow references. The clip-on enables precise flow measurement during inhalation due to the high sensor accuracy. MDI actuation timing was referenced to the flow profile, showing the drug was actuated on time. Several lung function values can be extracted and monitored over time. Smart inhalers will allow new possibilities for all stakeholders, from insurances, medical professionals, and patients, which should finally benefit from improved disease control. If you would like to get more information, please go to our inhaler website or contact me directly. Thank you very much for your attention.